Hello, AP Physics 1. So this will be my final video about the last two units you'll be tested on this year, which is simple harmonic motion, which we'll talk about first, and then finally rotational motion. We've done a lot of rotational motion recently. I'll organize kind of review sheet in a slightly different way if it helps you versus that translational rotational sheet we've been working with, and you can decide what works for you. Document camera here. There we go. Awesome. We still have audio and we're good to go. So let's talk about simple harmonic motion. When you deal with simple harmonic motion, you often talk about motion that graphically can be represented in this manner, where on your y-axis here is amplitude, positive, amplitude, negative, 0. And then on your x-axis is time. And then from there, of course, you have something that does this, like so, where from peak to peak, or from trough to trough, whatever, from here to here, because time is our x-axis. This is big T, or the period, the time it takes to go back to its original position, to go back to its positive amplitude position, to go back to its negative amplitude position. And as we go through the three examples of simple harmonic motion, I'll go back to this idea of amplitude and what amplitude means for these different cases. So we basically have three different cases in this classes. You have uniform circular motion is an example of simple harmonic motion. As an object goes around a circle, it comes back to its original location. You have, of course, springs that spring back to their original location. And then you have the pendulum, which swings back to its original location. Each of these have their own period formula. 2 pi divided by the angular velocity, or 1 divided by frequency, if it's uniform circular motion. If you're on a spring, notice we're TS now. It's 2 pi times by mass divided by K. Notice the one thing you don't see here, which is important, is any idea of X. How much you actually displace the spring. How much you displace the spring does not affect the period. Only the mass and the spring constant do. And finally, the period of a pendulum equals 2 pi, the length of the pendulum, divided by g, which is the acceleration due to gravity on whatever place you may be located in that particular problem. This, of course, is Earth. This would be 9.8 meters per second. So there are your period equations that you need to be aware of. And also, I'd make this connection back to amplitude. If you are talking about uniform circular motion, what is this amplitude? Whether it's the radius. Are you on the plus side of the radius or the negative side of the radius as you go around in your circle? In the case of springs and pendulums, we're often talking about the X. How much is the displacement? How much did you pull back the spring? How much did you pull back the pendulum? That is your X, and will show up here in this amplitude. But notice in both of these cases, that doesn't matter for period. As long as you don't go to extremes, you'll be good to go. When it comes to the pendulum, what matters is length and g. Notice, no mass. And those are the things I'll be focusing on. What's in these equations versus what's not. What affects period versus which doesn't. And then your graphical understanding. And that's simple harmonic motion for you. Not too complicated of a thing. We can also understand, and here's our last topic. This is rotational motion. Let me zoom out so you can get the, hopefully most of it here. There we go. There's my whole sheet. So this is another way of looking at rotational motion. We did that kind of translational. Let me quickly find that. Translational rotational sheet, which is certainly great if that's, you understand that. Look like this, translational versus rotational. You should have copies of that with the additional equations that you need to be familiar with. That's what we had created earlier. Or you can understand it in this. So in rotational motion, there's rotational equations for each topic we have this year. Here are kinematics equations. Here's for when angular acceleration is constant. Here's when angular acceleration is 0. Here's our force equations. Here, notice where force shows up as a component of torque, and that torque plays into Newton's second law here. The angular acceleration equals the net torque divided by rotational inertia. If you forgot what rotational inertia is, it's where the mass is according to its radius. And that's why it fits right here. Instead of being mass in Newton's second law, now we have I. Because in I, it matters where the mass is. Is it at the radius? Is it somewhere closer? That really matters in determining these problems. Kinetic energy, and then momentum. And you're going to see the same things pop up. Like here's the change in angular momentum equals torque times time. I can imagine a problem where they give you a graph that has time on the x, torque on the y, and the area under the curve, of course, is the change in angular momentum. Just like if they gave you a change in momentum problem, they would expect you to be able to take that force times time graph, take the area under the curve to get the change in momentum. The same things are going to pop up, just in a different place. Before we leave, the one thing you really want to keep in mind, let me try to get this back in for you, is when are we in rotational motion versus when are we in circular motion? And this is what I would think about. For circular motion, you're going to have one point object moving around in a circle. Here it's often different. You don't have one point moving around. You have something like a door rotating, a wheel spinning. There's masses all over the place that aren't just in one location at one time. And that's when really something is rotational motion versus uniform circular motion, which we did earlier this year. And it's solved in much different ways. So keep that in mind to separate those two topics in your mind. But that's all I have. And good luck.